Hello students, and welcome to the second lecture that we have for equilibrium. And this lecture is going to be on Le Chatelier's principle. And Le Chatelier's principle is going to essentially be a lecture thing or a concept that we are going to go over that kind of has us explain how we can affect equilibrium. And equilibrium is going to be something that we definitely want to affect, especially in the business world, because if we're trying to get a certain product from a reaction, we want to make sure that we are doing everything we can to maximize the amount of product in that reaction. And there's a couple of things that we can do to go ahead and manipulate the situation so that we get the right amount of products in each reaction. Okay. And so the first thing that we're going to do is we're going to go ahead and define Le Chatelier's principle. And Le Chatelier's principle basically states that if a system at equilibrium is disturbed by a change in temperature, pressure, or concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. All right? So basically what's going to happen is that if you input more product or you input more pressure or temperature, the reaction is going to go ahead and shift to try and equalize it and going to try and balance out what you have recently done to that equation. All right. And in this, when we go more in depth, it's kind of saying that we're shifting something with what's known as the equilibrium expression. Okay, so essentially what we're doing is we're putting the situation out of equilibrium intentionally. So we're pushing it one way out of equilibrium and then letting it reach equilibrium again. Okay. I don't know that I really like that one. Okay. And so one of the big things that we like to do to push things in equilibrium is that we like to use the Haber process. And some of you may be familiar with this from a previous lecture series on equilibrium. But the Haber process is a way for us to mess with equilibrium using a whole bunch of different things. The first thing that we typically like to do is we like to go ahead and say, okay, we have a reaction where we're trying to make essentially ammonia. Okay, and ammonia is one of those chemicals that's really, really important for two big things. It's important for farming because typically nitrogen in the soil is the limiting factor for much plant growth. The second is that it's also important for weapons production. Okay, and so this particular process, once it was found, it was able to essentially liberate a lot of countries from needing to barter for other ammonia sources. And because of its development, it directly led to essentially World War I and World War II, because Germany was able to make, bombs and enough food for its people and become a dominating economic power because it had essentially ammonia. Okay, and this particular reaction of N2 plus 3 hydrogens to make ammonia is a back and forth reaction. Okay, so this reaction occurs at equilibrium. Okay, but we don't want it to be at equilibrium. We have plenty of nitrogen, and hydrogen's really easy. We want to take lots of this, okay? So one thing that we can do is we can go ahead and say, all right, well, let's add some extra hydrogen here, okay? And in this graph that we have here, what you'll notice is that we're at an initial equilibrium, and then what we do is we add a whole bunch of hydrogen, okay? And so we're adding a whole bunch of hydrogen all at one spike, okay? And what will happen is that we're going to go ahead and move towards a new equilibrium. And the new equilibrium is going to be at a slightly different state, okay? So we changed our initial prospects. We've added more hydrogen. And when we do that, we end up making a little bit greater percentage of NH3, which is what our goal was. We wanted to make more NH3. So us being able to add hydrogen, if we add a reactant to the left, we end up pushing equilibrium more to the right. Okay? And so this right here is an example of what we do to go ahead and push this for the Haber process. Okay? And, let's see. Yeah, okay, it goes in here. So what we end up doing is we end up heating it up. We add a catalyst to make everything go faster. And then we end up compressing the gas so that we cool the NH3. So we're going to take NH3 out. And I want you to imagine that if we take a whole bunch of NH3 out, that we're not going to be able to make as much hydrogen, okay? If we remove from here, we'd have to add more to go ahead and balance it out, okay? So this is the whole process for the Haber-Bosch, and we'll explain the Haber-Bosch in a little bit more detail, okay? But for right now, we're going to go into depth about how equilibrium will change with concentration, okay? And when concentration of one or more of the reactants is increased, the first thing that you're going to notice is that, we've changed our conditions, therefore the system's no longer going to be in equilibrium. Okay. The position of equilibrium will move to the right to reduce the effect of the increase of the reactant. So we've added some reactant, we've added something to the left side of our equation. It's going to push the equilibrium to be higher towards the products to balance that out. Okay? And that's what the last dot is essentially stating. Whereas if we increase the concentration of one of the products, the equilibrium, we're no longer going to be at equilibrium, which means that we're going to have to go ahead and push it to the left in order to balance out to balance out the products, okay? Therefore, we'll push our reaction more towards the left, okay? So here we have an example, okay? And this is essentially acetic acid or ethanoic acid plus ethanol, okay? And this ends up making ethyl ethanoate, okay, and water, okay? And the concentration of ethanol is increased, okay? So, according to this, okay, according to Le Chatelier's principle, if we have this situation going on and we increase and we pour in more ethanol, then what's going to happen is that we're going to push this equation more towards the right, okay? So that means that we're going to end up getting more ethyl ethanoate as our product, okay? And that's how, essentially, we're going to use Le Chatelier's principle. Okay? Now, on the other side, what happens if we add more water? Okay? So more water is going to end up pushing this to the left. Okay? Therefore, we're going to have more of our reactants end up being made. Okay? So it's kind of like a teeter-totter situation, that if we add more to the left, the right-hand side is going to end up getting increased in order to balance that out eventually. Okay. The next one that we're going to work with is pressure. Okay. So pressure is another factor that is going to affect equilibrium, okay? And if you imagine that, things are colliding with each other, gases are constantly colliding with each other, if you affect the pressure, you're going to end up affecting the equilibrium, okay? And for how it's going to affect the pressure, you're going to go ahead and say that any change in pressure is going to shift the reaction towards the sides which minimizes the effect of the change in pressure. Okay? And what we want to actually think about that as is, okay, so which side is going to be affected by pressure the most, okay? And the easiest way for us to think about it is, all right, which side has more moles of gas? And the side that has more moles of gas wants to have less pressure, is going to excel in less pressure, whereas the one that has the least moles of gas is going to excel at high pressure, okay? So let's go ahead and show an example here, okay? And here we have an example where we have carbon dioxide plus 3 moles of hydrogen gas, and that makes ethanol in water. Okay. So in this case, we have 4 moles of gas that's on the left. We have 2 moles of gas that's on the right. Okay. If we were to increase the pressure of this jar, what'll happen is that because there's more gas on the left, we're going to push the reaction to make more products over here. Okay, so if we increase the pressure, we're going to push it so that we end up making more of the products that are on the right because there are less moles of gas. Likewise, if we decrease the pressure, what'll happen is that we're going to increase the amount of reactants that we have. Okay? The last thing that we can use for Le Chatelier's principle is temperature. Okay? And temperature is also a big thing for Le Chatelier's principle because if we modify temperature, a whole bunch of reactions will end up going, faster or slower. A couple of things to remember for it is that the increase in temperature is going to be the increase of all the particles in the surroundings and the particles themselves that we're concerned with reacting. And in Le Chatelier's principle, the reaction will go in the direction that opposes the increase in energy. So the reaction will go in the direction in which energy is absorbed, which is the endothermic reaction. Okay? So I want you to imagine that you have, this is kind of going with like the Hess's law reactions where we flipped reactions to go backwards and forwards. In this case, what we'll see is that all the endothermic reactions are going to be the ones that gain energy. So if you increase the energy of a system, the endothermic reaction half will end up going faster. Whereas if you decrease the energy of the system, the exothermic reaction half will go faster. Likewise, if you decrease the energy of the system, the endothermic reaction will go slower. And if you decrease the energy of the system, the exothermic reaction will go faster. Okay. So let's go ahead and take a look at this reaction right here, which is going to be HI, or hydrogen iodide, transforming to hydrogen gas and iodine. Notice that this forward reaction, okay, so going from 2 hydrogen iodines to hydrogen gas and iodine gas, is an exothermic reaction. Sorry, it's an endothermic reaction, which means that it takes in energy, all right? If we increase the energy, what will happen is that we're going to shift it to the right, okay? Because it's increasing in energy, okay? If we decrease it, we're going to shift it to the left. Whereas if you have an exothermic reaction, so for instance, SO2 plus O2 is an exothermic reaction. If we increase the temperature, what will happen is that it's going to shift towards the left or shift towards the reactants. So we'll end up getting more SO2 and O2 formed. Whereas if we decrease it, it's going to go more towards the right, towards SO3. Okay? And so that's what's going on with temperature and Le Chatelier's principle. Okay. And the last thing is a really small thing, is that a catalyst is not actually going to have any effect on the point of equilibrium. But what it will do is it will make it so that we can achieve this faster, or usually with lower amounts of energy. Okay? So just remember that as we go forward here. All right? Now that's going to end up closing us out for today's lecture on Le Chatelier's principle. You should be able to start working through your worksheet for this section. And then once you do that, you'll be able to start thinking about different ways that we can mess with Le Chatelier's principle and how it can be used to affect different chemical processes in the future. Until then, I want you to remember to stay lazy.